Okay class, I wanted to make a video showing a homework example of how to find measures of dispersion like the range and standard deviation when given a set of data. So here we've been given a very small set of data with just 1, 2, 3, 4, 5 items. So we would say that the sample size for this example is n equals 5. So keep that in mind. And you're welcome to sort the data if you like from small to large. So if you resort it, you'd have 6, 9, 10, 11, 14. That's the sorted version, right? Okay, sorted data. So what we're looking for here in measures of dispersion, unlike measures of central tendency where we're more interested in what's happening in the center of the data, like right in the middle, which here again would be the median 10, instead we're more interested in what's happening at the extremes, or how spread apart is our data. You can see that these data numbers are not very spread apart. If, for example, I gave a test and someone scored 2%, but someone else scored 100%, that's a big spread. Like that would be a spread or a range of 98. But in this case, you can see that the spread is not very far. 6 to 14 gives us an idea that our range is not very big. So remember how to find the range. Very simply, you take your highest value minus your lowest value. So in this case, you take your 14 and subtract your 6. So this would have a range of 8, and if you went to one significant digit, that's 8.0, and if you went to two significant digits, that'd be 8.00. Okay, so that would be our first measure of dispersion. That's the easiest one, simply the high minus the low. But for the standard deviation of a sample, and that's what this is, it's a sample of data, it's not the whole population of data. We had a formula for standard deviation in our notes and in our homework, in our textbook, and that was the standard deviation of a sample is known as the letter S, and it was the square root of the sum, that's what sigma means, of the squares, that's what this looks like, of the parenthesis. The square of what? The differences between each x value, each of these are x values, each data value is an x value, and the mean, the sample mean is x bar. So what that's saying is, if you first figure out what the sample mean is, x bar, what's the difference between each of these original values and the mean? How far away is it from the mean? That would give you an indication of how spread apart your data is from the center. So we're going to find those differences, we're going to square them, because sometimes the differences are positive and sometimes they're negative. Squaring them helps us to compare apples with apples. And then add the differences up, and instead of dividing by the total number of data values, n, since this is a sample, we build in a degree of freedom here to help with our accuracy, and this is n minus 1. So if you have looked at your notes, you'll notice that I like to break this into steps for you, where I tell you that first things first is you want to figure out what is your mean. So you find x bar. So to find x bar, that's just the sum of the values, the sum of the x values, data values, divided by the total number of values, the sample size. So we need to add up either the sorted version or the unsorted version, the original data values, and divide by the number of them. So in this case, 10 plus 9 is 19, plus 6, we're at 25, plus 11, plus 14. And what do we get? If you said 50, you're correct. Divided by the number of items, which was 5, and we're getting a nice number, a nice whole number. Sometimes it'll be a decimal, but in this case, it's just the number 10, isn't it? Or 10.0. So that's the average value of this data set, okay, 10. It just so happens it's also the median, and when the measures of central tendency line up like that, it could be an indication that we have a normal bell-shaped distribution, which we'll be studying in our future section. Okay, so now that you found the mean, you've done step 1. Step 2, if you have your notes in front of you, was to make a comparison, right? We're going to compare the distance of each of your initial data values, either sorted or unsorted, with the mean itself. So now we have the mean. That's this part of the formula here. Okay, and now what we're trying to figure out is how far is each data value from that mean. So let's go ahead and make maybe a chart. I suggested this in your notes. So if you make a little chart here, I'll come over here so you can see better. So in step 2 here, we're going to say how far is each data value x from the mean itself. So let's grab our blue again, just to be consistent for you. How far is each data value from the mean? And we're going to call this our second step. So step 2, if you will, is right here. And I'll leave some space. So we have a total of 5 data values, so I'm going to have 5 rows. Leave a little room there. And I could complete the chart if you want it to look pretty. Not the prettiest, sorry. So what is our first data value? Well, if I use the sorted version, it's 6 minus the mean. Then the next one is 9 minus the mean. The next one was 10 minus the mean, 11 minus the mean, and 14 minus the mean. So those are each of your data values, and we're simply subtracting the mean to see how far apart they are. Now, I have no doubt that you could do a lot of this, that you could do a lot of this in your head, okay? But it is a very good idea in my experience to write it down. So let's go ahead and write down minus 10, 10, 10, 10, 10. Okay, again, if you had decimals, you'd include those, of course. So when we do this subtraction, let's see what our results are in this step here. When we do the subtraction, what results are we getting? Do you see it? Well, in the first case, we get a negative number, don't we? We are getting -4. In the second case, sorry, it's a little rough to look at. Let's make some more space here. Zoom out. So we got -4. In the second case, 9 minus 10 is -1. In the third case, 10 minus 10 is 0. In the fourth case, 11 minus 10 is +1. And in the last case, 14 minus 10 is +4. So that brings us to our third step. Why do I need to square those differences? Well, because some of them are positive and some of them are negative. And so in order for them not to wipe each other out, if you were to add, for example, a -4 and a +4, or a -1 and a +1, they would cancel each other out. So that is why we have step number 3. So what does step number 3 do? In step number 3, that's where we square the differences. So that's where this part comes in. Okay? So to square those differences, we take what we had in the last step and we square them. So we're going to say to square those differences, x minus x bar squared, we're going to take -4 and square it. And what does that give me? -4 times -4 is 16. We're going to take -1 and square it. So that's +1. We're going to take 0 and square it. That's 0. 0 times 0. We're going to take 1 and square it. When I say square it, I mean multiply by itself. 1 times 1 is 1. And we're going to take 4 and square it. And 4 squared is 16. 4 times 4. Again, the purpose of that is now we don't have any negative and positive differences that would cancel each other out. So once we've done that, we are now able to add them up and not have them cancel, which is pretty powerful. So we are now ready for step number 4 of this formula. So what is step number 4, if you're wondering? Yeah, step number 4 is the summation. It's the sigma. We are now going to be in a position where we can add up those sums, those squares. So this is step number 4, if you will. We're going to add up those squares. So 16 plus 1 plus 0 plus 1 plus 16. Well, I know 16 plus 16 is 32. 1 plus 1 is 2, and 0 doesn't add anything. So 32 plus 2 is 34. So the sum of those differences is 34. So now I'm here. I have my entire numerator. So if I were to fill in what I have right now into my formula, if you're a formula type of person who thinks it's easier to plug things in, here is where we're at. So in our formula, we now have S for the standard deviation of the sample equals the square root of something over n minus 1. But we now know our numerator because we did all the work. We found that the sum of those square differences was 34. So that's what we get to put in our numerator. So we stick the result of step 4 in that numerator. And now you are at step number 5, which is to figure out the denominator. This part should be pretty simple because we started off earlier figuring out what n was. N was the number of items in our data set. In other words, our sample size, which was 5. So step 5, if you will, is to figure out what n minus 1 is. And we know what that is. N in this case is the number of items that there were, 5. So here we have 5 minus 1, which is really, go ahead and erase it if you can, 4. So now we have calculated the denominator. We got n minus 1 is 4, 1 less than the number of values that there were present. We build that in for a sample to be more accurate. And finally, you're welcome to put that in your calculator and see what you get for step 5 here. 34 divided by 4 is what number? Did you get 8.5? Okay, so if you answered 8.5 as the standard deviation, you would not be correct. That's actually the square of the answer. That's called our variance. We'll study that in statistics more formally. But our final answer is the square root of that number. So for step 6, you're finally now able to take the square root of that number and say the square root of 8.5 is approximately, once you take the square root, what number? 2.915 roughly. I believe my calculator says after the 5, 4.75947, and they'll usually ask you to round to 2 significant places. So you'd probably make this, since this number here 5 is 5 or higher, you would actually make this a 292 typically. Okay, so it depends where they ask you to round, but that would be our standard deviation. And if you go back to the notes, the videos, and to the ebook, you will notice what standard deviation is telling us is that on average, each of these data values is almost 3, since 2.92 is close to 3, is almost 3 units away from the mean. So on average, they're about 3 away from the mean of 10. And that, it kind of makes sense because these numbers aren't super far apart from 10. For example, if I gave a test and the average or the mean on the test was 70%, and you scored, let's say, a 90% on the test, which is 20 points away, if I told you that the standard deviation for that test was, let's say, 15 points, then you scored beyond that. You scored 20 points. So to do above the standard deviation, it tells you you're pretty far away from the mean. So you're pretty away from where most people are, okay? And so we use standard deviation when we're trying to compare values compared to the population. And we can describe it using bell curves and other things that we'll talk about in future lessons. Well, I hope this was helpful to break down the formula for standard deviation into steps. If you're highly visual, I hope you found this chart to be helpful for you. If you have further questions, feel free to email me with them. Otherwise, happy practicing. And remember, math is not a spectator sport. I'll see you next time.